Jack Jackson. In this video, we're going to briefly review an F distribution, some of the probability characteristics there, computing probabilities and inverse probabilities, and we're going to need this to do inferences about two sample tests and intervals for standard deviations. So just to remind you very quickly, this test statistic that we're looking at now is S1 square over S2 square, where S1 is the standard deviation of the sample 1, S2 is the standard deviation of sample 2. For this to work, the two populations, both of them, have to be normally distributed, and we can compute this statistic here, this F statistic. The F distributions are family distributions, and they depend on both of the two sample sizes. So we call these things the degrees of freedom. Degree of freedom 1 is sample size of the first sample minus 1, and degrees of freedom 2 is sample size 2 minus 1. Sometimes the degree of freedom 1 is called the degree of freedom for the numerator, and the degree of freedom for the denominator is what I'm calling degree of freedom 2. So we have those two things here, and so sort of obvious that why they use numerator denominator. Numerator is the top part of the fraction, which is where your sample 1 statistic is. Your sample 2 statistics in the denominator, so that's why this one is for denominator. The degrees of freedom for the denominator. The PDFs of these distributions are very similar to chi-square distributions. They're first quadrant only graphs. They're not defined for negative inputs, or they're 0 for negative inputs. We start at the origin and go up to maximum and then trail out to an asymptote of 0 on the right. So they're skewed, and they're also skewed to the right. Go back to unit 3, where I talk about this some more if you want a little bit more than I'm going to give in this very brief overview in this video. Here are a couple of examples, or one example, I guess. Take samples of size 15 and 20 from two normally distributed populations to compute their sample standard deviations. Then compute the test statistic S1 square over S2 square. That ratio of variances has an F statistic with 14 and 19 degrees of freedom. 14 and 19 were obtained by subtracting 1 from the two sample sizes. We can graph the PDF, as you see here on the left, by an F PDF of X with the 14 and 19 degrees of freedom in that order. Gives us a graph looking like this. This thing that's blacked out here is actually 0. So from 0 to 4, it gives us a decent window. And at least on the one on the right, it goes from 0 to 1. I'm not sure if it's using the same window on the one on the left. It may. The CDF here is just FCDF from 0 to X, 14, 19. And, of course, like always, it starts at 0, stays real small for a while, then comes on up. And actually right where this one hits a maximum is where this one has an inflection point from concave up to concave down, right side up bowl, upside down bowl. And it levels out then at 1 eventually. So like all CDFs, it goes from 0 to 1. Here's the same thing on a, along with some sliders and things, on a TI Inspire. So you can see here a TI Inspire calculator with this built up, and you can build these things up with sliders and things. So one function I have graphed is the FCDF from 0 to X, degrees of freedom in, degrees of freedom numerator and denominator there. And the blue one is the FPDF. Yes, so it looks like this is the same scale here. And I can move the degrees of freedom there and here as well. You can see that this is a graph of y equals 0.5, and we can see where that touches the red CDF graph is right here. So this x value is the median right there. So you can see it's about 1.03 at the moment. and that's changing slightly as I move this around. And then this one is the mean right here, and is changing here. It's not changing here. So it turns out it only depends on the degrees of freedom on the denominator. But you can kind of see what some of these different ones look like. And it's changing one or the other of these things around. Turns out there's a nice little formula for the median, or for the mean. It's degrees of freedom of the denominator over degrees of freedom of the denominator minus 2. So the mean is only affected by this one here, not by the other one. Okay. All right, now let's compute some probabilities. Compute the probability that f is less than 0.7 from this distribution. That our f or x value is less than this. You should know how to do this. Press pause and come back when you have the answer. Well, it's just a CDF for doing probabilities, and we know how to do this, so it's just an FCDF. Less than 0.7 starts at 0, goes up to 0.7 for lower and upper. Degrees of freedom for the numerator is 15, and for the denominator it's 20. That's incorrect. You need to have the degrees of freedom to be one less than the sample size. So I'm going to do something you can get away with when you're the teacher. You can't do this on a test, but I'm just going to change the problem to match what I have. Suppose the sample sizes are 16 and 21. So we'll change the problem to that. And then now my degrees of freedom are right, 15 and 20. And that is my probability there, approximately 0.2430 to 4 places. How about an inverse probability? Let's still say sample size is 16 and 21. So again, we can use degrees of freedom of 15 and 20. I should say this is an F, 15, 20. So anyway, let's do a critical value here. Compute a C value, so that the probability that F is less than C is 0.05. Of course, this is an inverse probability calculation, so you run inverse F if we have such a thing, or if we don't, we can do it with our per-calculator program. Program inverse F. A cumulative probability is 0.05 is to the left. 15 and 20 for the 2 degrees of freedom, and it outputs the probability we're looking, or the critical value we're looking for, which to 4 decimal places is 0.4296. If you don't have this calculator program, what you have to do is graph the FCDF with these sample sizes, or these degrees of freedom. Then graph y equals 0.05, calculate the intersection, and the x value should be that. So you can do it that way if you don't have the program. The program is quite a bit easier if you have it. So there's a quick review of F distributions. Again, if that was too fast, please go back to Unit 3 where we did this the first time, and you can see several more examples, and this worked out a little bit more slowly.